Hello, everyone. In this class, I wanted to discuss discrete random variables and distributions. One way of looking at why we study probability is the following. Say we observe many random phenomena, and we sort of they're similar, right, in some sense, and we single out some uh, uh, intrinsic feature of these similar phenomena, and sometimes we call use a random variable to study these intrinsic feature. And then we study the model, which is in probability usually meaning distributions. And then we study the properties, try to find the probability of certain events, and then study the parameters, etc. Then we use these properties uh, and these tools to different similar random phenomena. Okay. The models will be discussed in another class, but for this class, we're mainly focused on introducing the concept of random variable and the concept of distribution and some important parameters. All right, so what is a random variable? It's quantities of interest and often real valued functions defined on the sample space. So for example, if we toss a coin and we have a sample space of heads and tails, yeah, that's the sample space. And sometimes it's easier to talk about numbers, real valued functions, than talking about heads and tails for other examples like colors and so forth. It's easier to talk about numbers, and you will see the benefit slightly later. So we define a random variable x, and you can define this random variable to have value 1 if heads show up, or 0 if tails show up. Okay, so this is a random variable. Another example, say if we roll a die once, suppose it's a six face die, and then you have 1, 2, 3, 4, 5, 6. And this is our sample space, and we can define y to be exactly these numbers. So 1, if 1 shows up, and 2 if 2 shows up, and so forth. So, quite common. But sometimes if we are interested in certain function of these numbers, for example, square of these numbers, then you define a different random variable. Okay, so it depends on what we're interested in doing. Roll two dice and the sum is considered. Again, sums are numbers, so we can just define the random variable which is the number is the sum. Okay, so if sum is 2, then we're gonna just define the random variable to have value 2. So in this case, we sort of equate the sample space of the random experiment and the sample space of the random variable. The sample space of random variable is the sum, sorry, no, it's the set of all possible values the random variable can take. So if we toss a coin, you define 1. If head shows up, and define 0 as the value of the random variable. If heads show up, then we have a sample space of the random variable 0, 1. And for when we roll a die and then consider the number showing up, and we have 1, 2, 3, 4, 5, 6 as the sample space of the random variable. And it's kind of important to be able to figure out the sample space of a random variable, and then we are able to figure out the probability distribution again and so forth. So this is sort of the first step when you try to find out the model of a random variable. The first step is to figure out the sample space of the random variable. So here, if we roll two dice and sum is considered, and then the sample space of the sum, okay, it's the random variable, is 2, 3, and so forth to 12. So that's the sample space of this random variable, which is the sum of two dice. Next one, so if we toss a coin 10 times and the number of heads is considered. So here the number of heads is the random variable, and the numbers itself is a real valued function. Actually, it's an integer, positive integer here, non-negative integer. Okay, so it's a random variable, and the sample space of this random variable. You toss a coin 10 times, the number of heads. It could have no heads, so 0. 1 heads, so forth. You have 10 heads. So that's the sample space of this random variable, which is the number of heads in 10 tosses. Later on, we study the distribution. And for the moment, we're trying to get used to the concept of a random variable. The next example, toss a coin till we see the first heads. So you toss a coin and you see if it's heads or not. If it heads, then it's 1. Okay, you stop. So the value of the random variable is 1 if you see the first heads on the first trial, on the first toss. And if the first one is tails, and then you move on to the next one and you see a heads, then this number of tosses needed to see the first heads would be 2, and so forth. Okay. So here we are actually talking about the number of tosses needed to see the first heads. And then the number of tosses, it's a real valued function. It's a random variable. Get the sample space 1, 2, 3, and so forth. I guess this is the concept of random variable. The examples I gave earlier, they are so-called discrete because the sample space is a discrete set, possibly countable because you have possibly infinite countable, like 1, 2, 3, 4, and so forth, to known without a bound. The next example, select a person and height is measured. And in this case, normally we treat people's heights as a continuous random variable, say from 0 to maybe 3 meters. It's less likely to see 3-meter person, but nevertheless, you sort of having a interval. Okay, so it's continuous. So these are discrete. And this one is continuous. Normally. So this is the concept of random variable. Next, we study the probability mass function. It's usually denoted by f of x. And the meaning of fx is f of x if we have a random variable which has a PMF of fx. This is the notation I use to denote that a random variable capital X having the probability mass function, little f of x. Then the meaning of f little x is just the probability that capital X takes value little x. In probability, we usually distinguish these capital X and little x clearly. So this is random variable, and this is a value that random variable can take. All right, so they have a sort of different meanings. Because these are probabilities. Oh, by the way, this is an event. Okay, this is an event. So it's a probability. So little fx would have to be non-negative, uh, possibly zero, right? But non-negative, it cannot be greater than one. So it's greater than equal to zero, less than one. When we talk about math probability mass function, normally we just specify the x values that and the probability is not zero. Okay. Um, the summation of fx for ox, this notation is the summation notation. Okay. Sum up all the fx for ox is always 1. This satisfies one of the axioms of the concept of probability. The probability of the whole sample space is always 1. All right. So let's have a look at the examples we talked about earlier. So at the beginning, we have just toss a coin. You have a sample space of 1, 0, right? Define the random variable to be 1 if heads show up and 0 if tails show up. So that's the example we're talking about. Now, in order to find a probability, we need to really say the coin is fair or not. And say, suppose it's a fair coin, then you have half chance to get heads and tails. So we can express this distribution as a table. So this little x, this little fx, and you have 0 and 1. 1 means heads, 0 means tails, and it's fair. So we have these probabilities, and the summation is always 1. All right, next we roll a die. It's a fair die, so the probability of getting 1, 2, 3, 4, 5, 6, they're all the same. So you can use this one. We can actually use a function to describe. It's probably easier to do that. We know the sample space is 1, 2, 3, 4, 5, 6. So we can just say fx equals 1 over 6, and x equaling 1, 2, 3, 6. So it's a probability mass function. It has mass on these values 1, 2, 3, 4, 5, 6. Such a distribution is called a uniform distribution. It's discrete, so it's discrete uniform distribution. The probability of each outcome is the same. Move on to the next one. Let's say we roll 2 fair dice and the sum is considered. We talked about the sample space, which is 2 to 6, 2 to 12. So let's list all these outcomes and then we try to get the probabilities. You have x, you have fx. X could be 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, and then 12. On the probability, the sum is 2. The only chance is 1, 1. And totally, there are 36 outcomes. Okay, there are outcomes of rolling 2 dice. So here are the two sample space we're talking about. One sample space is just the outcome of rolling 2 dice. So you would have a 1, 1, 1, 2, this kind of outcomes. And totally, you have a 36 outcomes. These are they form one sample space when we talk about the outcomes of rolling 2 dice. These are the outcomes and they form a sample space. And then another sample space we're talking about here is the summation of the numbers shown. And the summations are 2, 3, 4, 2, 8, 12. This is also the sample space of the sum. All right, so the sum is 2. That means you only have one outcomes from rolling two dice, 1 and 1. Okay, so it's 1 out of 36. And to get the summation of 3, you have two possibilities, 1, 2, and 2, 1. All right, so sometimes you can list all the outcomes, the 36 outcomes, and you just look at the summation, and it's pretty easy to count. If summation is 3, these are the two possibilities. So it's 2 out of 36. Uh, Notice here we're rolling two fair dice, and all these outcomes are equally likely. So you only need to count how many outcomes in this sample space, the sample out of 36 outcomes. Okay, that's all right. 4. So 4, to get a summation 4, you have a 1, 3, 2, 2, and a 3, 1. So the 3 out of 36 and so forth. Once you hit 7, you have a 1, 6, and you have 6, 1. Here's 1, 6. And then you have a 2, 5, 5, 2, 3, 4, 4, 3, and 3, 3. Sorry, 3, 4, 2, 5. So totally of 6 of them. 1, 6, 6, 1, 2, 5, 5, 2, 3, 4, 4, 2, 4, 3, and 6 of them. Now, when you hit 8, the summation is 8. You don't have 1, 7. Okay, you don't have 7 because common dice, fair dice, have 6 faces. So you have 7. Actually, you sort of having smaller cases, a smaller number of outcomes. So when the sum is 8, you actually have 5 of them. And then you have 4 of them, 3, 2, and 1. Right? You add all these probabilities, you will get 1. If you're interested, you can check. We're not doing that here. Next example. Toss a fair coin 3 times, and the number of heads is considered. So the random variable is the number of heads in 3 tosses. So we have 0, 1, 2. 0, 1, 2. So this is our x. And we try to figure out the probabilities. All right, so 0 heads, that means all tails. It's a fair coins, all tails, tail, tail, tail. The probability would be 1/8. Here we actually assume that all these tosses are independent on each other. Okay. That's assumed, otherwise you really cannot do anything. But for example, you toss a coin, you see if heads, and the next one, deliberately make it heads. That's totally not the case here. We're assuming all these tosses are independent of each other. So you have a tail, 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 so half times half times half. If there are 2 heads, 3 times, sorry. 3 times, actually you have possibility of having 3. So if you have 3 heads, and similarly you have 1 ace, half, half, half. Now, 1 heads in 3 tosses. So you could have heads, tail, tail. You could have tail, heads, tail, and you could have tail, tail, heads. You actually have 3 possibilities. Each one has probability 1/8, so 3/8. Similarly, for 2 heads, you could have tail, heads, 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 tail, heads, 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 tail. 3 possibilities, 3 out of 8. and you add them up, you'll get 1. This is one special case of a coin tossing uh, n times. Okay, it's we can model it by using binomial distribution, which is discussed in a different class. So I'm just using it as an example to introduce the probability mass function. All right, next one, toss a fair coin till we see the first heads. We know the sample space is 1, 2, 3, 4, whatever. All right, so let's try to figure out f of little k. So meaning is x equaling k. X is the number of heads, the number of tosses needed to see the first heads. So we study this event, x equaling k. What does it mean? It means the first heads is shown on k's toss. Because the first heads, that means the previous k minus 1 tosses which have tails. So x equaling k is an event. This is equivalent to saying that the first k minus 1 tosses yield tails, and the k's toss yields heads. That's exactly what this event means. Now we can figure out the probability based on this understanding. Again, when we toss a coin, we assume independence. So the first k minus 1 tosses yield tails half to the k minus 1. And then last toss is heads times half because it's a fair coin. So it's half to the k. If it's not a fair coin, then these numbers may be different. But you add them up, add these numbers, you will always get 1. Okay. More general example may be in the following slides. All right. Let's introduce the concept of a cumulative distribution function, CDF. It's called a CDF. Usually we use capital F to describe CDF and little f to denote PMF. So the meaning of fx is the probability that capital X is the random variable less than or equal to the value that the random variable can take, which is little x here. It's cumulative, so it's less than or equal to. Another way to think is f of some k, k should be less than or equal to x. That's what it means. All right, so let's look at an example. Toss a fair coin 3 times, and x is the number of heads. We just did that, right? You have 0, 1, 2, 3 with the probabilities 1/8, 3/8, 3/8, and 1/8. Okay, so this is x and this is little fx. So that's the PMF, is the PMF. So CDF, the CDF would be 0 up to when x is strictly less than 0. And then you have fx equals 1/8 when x equals 0. When x is equal to 0, actually is greater than equal to 0 or less than 1. I want to show you a graph which describes the PMF. Okay, that's we call the distribution histogram of the distribution of this random variable. So it's probably easier to see the situation, to see the relation between these two, the PMF and CDF. All right. So we have y, which is the probability. X is the value that the random variable can take. You have 0, 1, 2, and 3. Okay. Let's call this 1A's, 2A's, and 3A's. Okay. When we draw the histogram of a distribution, we make a bar such that the endpoints of this bar would be half between. So this is a half, this negative half. But really, we just talk about it's the histogram. Sorry. All right, let's start again. Let's draw the histogram of the of distribution. Let's draw the PMF on a graph. Y is distribution, X the value that the random variable can take. Okay. It's PMF, so when X equals 0, we have let's hold on a second, let me, it's 1/8, 2/8, and 3/8. Okay. When X equals 0, the height is 1/8, so we draw like that. And when X equals 1, we have 3/8. And then we have that. And this is not a histogram. Histogram actually you have a bars, but for the moment, I wanted to show you the relation between the mass function and the cumulative distribution function. So this is a PMF, 1/8 for 3. And CDF, uh, where do I draw it? All right. Ideally, I just follow below this PMF, but I think it should be fine. So it's a probability, and then we have X. Let's start with 1/8, and 2, 3, 4, 5, 6, 7, 8. It's 1. This is 1/8. 0, 1, 2, 3. The CDF, again, focus on the word cumulative. Okay, cumulative. When X is less than 0, certainly you have 0. There's no mass from negative something to 0, but you have a hole here because when X equals 0, we have a jump here, something like this. We would call it continuous from the right side. Okay, now you have that. And then at point 1, at x equaling 1, there's a jump because there's a mass at 1. You add this mass to 1/8, you would get 4/8. 1, 2, 3, 4. So you have that 4/8. And then nothing, no mass between between 1 and 2. And at 2, there's a jump because there's a weight, there's a height here. There's a mass here. So the jump of 3/8 as well. So you add 3/8 to 1/2, you get 7/8. Okay, and then no mass between 2 and 3. And there's 3 at 3 you have a jump of 1/8 because you have a mass at 3. And then you have 1 forever. Okay, so this is the CDF. If we mark it, then we use function to denote it, then you really need to list all these possibilities. Let me write down somewhere else. Okay, so f of x equals 0 when x is less than 0. And 1/8 when x is greater than or equal to 0, less than 1. And you have 1/8 plus 3/8, so that's 1/2 when x is greater than or equal to 1, less than 2. And then you add 3/8 at x equaling 2, less than 3, you get 7/8, and then when x is greater than or equal to 3, you get 1. So this is the complete CDF. I want you to notice that the CDF is always non-negative. Okay, it's always non-negative. Sorry, it's always non-decreasing. It's always non-decreasing. Negative, non-negative, that's obvious. But the feature is that it's non-decreasing. Uh, we say non-decreasing because sometimes different books will have different meanings when we say increasing. Okay, sometimes people denote increasing something like that, but some textbook allow flat things for it to be increasing. So increasing sometimes uh, there's different meanings in different textbooks. But non-decreasing is pretty clear. It's not decreasing. So that will allow a function to have flat line. All right. So that's a CDF for this example. If you know CDF, you should be able to find PDF. You just look at where the CDF has jump. If there's a jump, that means that random variable has a mass of probability at that point. And so I'll give you some very simple examples. So let's say fx equals 0, x less than 2, and then you have a 1/2 x greater than or equal to 2 less than 3, and then you say 1, 1, 1, 1, it to be bigger. So 2/3 when x is greater than or equal to 3 less than 5, and then say 1. Make it a little bit simpler, x greater than or equal to 5. So you wanted to see where the CDF has a jump. So at 2, there's a jump. So I have f of 2 equals 1/2. And there's a jump at 3, f3 equals, f3 is actually not equal to 2/3 because capital F3 is a cumulative function. Little f3 is the mass at 3. So you need to subtract half from 2/3. So 2/3 minus 1/2, which is 1/6. All right. And am I right? Uh, yeah, that's 1/6. And then there's jump at 5. So f of 5, little f of 5 equals 1 minus 2/3, which is 1/3. Okay. You added these three, you would get 1. Okay. But there's no guarantee that little f is non-decreasing. Okay. And let's talk about the histogram of a PDF. I sort of uh, wrote a little bit earlier and then I erased because I wanted to introduce the concept, the connection between PDF, PMF, and CDF, not focusing on the PDF. Sorry, I'm not focusing on the histogram. So the histogram actually normally we have the bars. So let me redo the previous example. One ace, three ace, three ace, and one ace. Let's do that. Okay, the histogram and just the graph of PMF. Sometimes they have a different features, different meanings. So the histogram of the previous example. And I think I draw a little bit, then I erased it, give up. 0, 1, 2, 3. Okay, so we have one ace here, and then you have two ace and three ace. I think three ace the top probability, the highest, largest probability of those outcomes. Outcomes of the random variable, which is 0, 1, 2, 3. Okay, so we draw bars. Okay, let's use this color. Okay, draw bars. It will be halfway, so in the middle point of these intervals. It's halfway between these integers 0, 1, 2, 3 here. So you have this one, and then you have a 1/3, and also 1/3. Well, not 1/3, 3/8. Sorry, my bad. Okay, so that's the histogram of this distribution: 1/8, 3/8, 3/8, 1/8. Once we have histogram, we can talk about the shape. Like this one is symmetric, and not that much symmetric, and there are two modes, 1 and 2. The sum of dice, two dice numbers, we have a 1 out of 36 and 2 out of 36 and so forth. So it's a little bit tedious to draw, but maybe I'll show you a little bit. Maybe it's also symmetric. You will see that very quickly. We have those values of the sum, which is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So 136, so that's called 136. Take on that, and 236. And probably I'm not drawing on scale. The tallest one is like the 6 out of 36. So it's like a step here, steps. And then you move down. Probabilities are smaller. Uh, okay, so it's 136, even though they look different, but well, I'm not drawing on scale. It should be symmetric. Okay, this is a 1 out of 36. One feature about histogram I wanted to mention, I actually forgot to say it earlier. The reason we put the bars on the midpoints of these integers is that it always has the base uh, width to be 1. So width would be 1. This width would be 1, and this width would be 1. And height is always the probability. So we can talk about the area. The area of this little rectangle would mean the probability. And similarly, you have the probability of getting 3, which is exactly the area of this bar. So you add all the areas, you always get 1. So this is an important feature about histogram. We deliberately made the base to be 1 and height to be the probability. So the area becomes the probability. So when we talk about probability, we just talk about the area. For example, for this example, the probability of x greater than equal to 4 less than equal to 7, then you just find the area, at least from the graph. That's what we can do. This is important when we talk about using continuous distribution to approximate discrete distribution. Okay, this concept is kind of important. So the area of the sum of the areas of these 4 bars will represent this probability. All right. What's next? Let's move on to the uh, the parameters of a distribution, mean or expectation. This concept, there are different meanings: mean, true mean, population mean. These are normally used in statistics. Uh, this one sort of half either way, probability or statistics. We use it, but expectation is normally used in probability more often. Okay? I'm not saying you cannot use this expectation in statistics at all. It's just the more often we use expectation in probability theory. So suppose we have a random variable x having a PMF little fx. Is the expectation is denoted by e of x. Some textbooks put parentheses there, but I normally don't do that. That there's another notation which is mu. They are both commonly used. E of x and mu, they're both commonly used. Mu again is probably more often used in statistics. So this quantity is defined to be the summation of little x times f of x, and you sum up for all x. So you can treat this summation as the weighted sum of the values the random variable can take, which are x, right? With weights of x, which is the probability. So it's the weighted sum of x with weights probabilities. So here we have several examples. So Bernoulli, what does Bernoulli mean? A Bernoulli random variable means that the random variable takes values 0 and 1, like a coin tossing problem. All the random experiments that have 2 outcomes, we can put them into this category, Bernoulli. So go back to the very first slide when we talk about the purpose, right? So you have all these random experiments that have 2 outcomes, say pass fail, success fail, uh, white, black if there are only 2 colors. All these random experiments or random phenomena, as long as they have 2 outcomes, we just model them by Bernoulli random variable. Okay. So the basic Bernoulli random variable has distribution 1, 0. These are the fx. And fx, we just put little p here and 1 minus p. So we'll call p is the probability of success, and 1 minus p is the probability of failure. And then E of x equals 1 times p plus 0 times 1 minus p, which is p. So p is also the mean. So the probability of success is also the mean. On American roulette, there are many bets you can talk about in many distributions. We're talking about here at the simplest situation, that is you bet on the color. So American roulette has 38 numbers. You have a red, six, actually 18 red numbers, and you have 18 black numbers. And then you have two green numbers, 0 and 00, two of them. Uh, well, in fact, it's just even though they denote they are like 0 and 00, as like they have nothing, no significance. But actually, this is the main thing that makes the game not favoring us. So, okay, so here is an example. You bet on a color. Say you bet on red. Here you bet on red. You bet $1 on red. And if it turns out to be red, you get $1 back and you earn another $1. That's the normal case. If it lands on black, then you lose your $1. If it lands on green, zero, zero, zero. You also lose $1. So let's consider the net return. So net gain is our random variable. Okay, net gain is our random variable x. So you can have $1 earnings, $1, or you can lose $1. So these are uh, the outcomes of this random variable, or the sample space of the random variable. And then we talk about the probabilities. This is little x. This is our probabilities, fx. You bet on the color, but bet on red. So the probability that it lands on red is 18 out of 38, because totally you have 36 plus 2 numbers. And the probability of losing $1 is 20 out of 38. So you add probabilities, you get 1. Okay, so let's calculate the mean. E of x equals 1 times 18 out of 38 minus 1 times 20 out of 38. That's uh, 1 out of negative 1 out of 38. That's dollars. Okay, that's negative dollars. I think it's about 5 cents, a little bit more than 5 cents. Uh, the meaning of this number is very clear in this example. Sometimes it's not that clear, and it's harder to explain using the real the daily life language. But this one is very clear. So I wanted to talk about the meaning, and it's a long sentence, but it really it says a lot of it says everything about what it means here. Okay, for this number, negative 1 out of 36, 1 out of $38. What that means? What does it mean? So it means the following sentence. In the long run, we are losing on average about losing, so I'm going to put positive sign because we are losing. So it's about 5 cents, right? 1 out of $36, 1 out of $38 on each game. Okay, so there are three points I want to make in this sentence. First of all, it's in the long run. You toss one time, you gamble one time. Really, the expectation doesn't mean much. So in the long run, And while losing on average, it's on average. It's not on a particular game. On particular game, either you lose $1 or you gain $1. You will never lose 5 cents on each individual game. So it's on average. And this number is on each game. So in the long run, you're gonna lose, or we're gonna lose so much money on average on each game. So that's exactly the meaning of this expectation under these circumstances. All right, so that's for American roulette. The other examples, yeah, let's talk about the other two examples because sort of they have different flavor, a little bit different, I guess. This one's very different, but let's talk about B two third, one third. Oh, actually, we didn't talk about it, so let's. What it means is binomial. It's just a notation. I'll tell you what the distribution is. This is the total number of tosses, which is 2, and this means the probability of success, be it heads or tail, I don't care. One third. So P is one third. So uh, what I mean is by this notation is the following distribution. Okay, that's what I mean. So B two tosses you have so the number of heads say you have 0, 1, 2. Uh, let's call it let's call head success. So 2 is the total number of trials. This is the probability of success. S is a success, not the sample space. Zero success. That means two failures. You have a 2/3 squared. That's 4 9s. And two success, that's 1/3 squared. That's 1 9s. And one success, you have success failure and failure success. Success failure has probability 1/3 times 2/3, and failure 2/3 times success 1/3. So it's 4, 2 9s times 2, yeah, 4 9s. Okay, so this is the distribution of this. Well, yeah, B actually is a distribution, so it's a table of this distribution. All right, though we can talk about the mean expectation. By definition, E of X is the weighted sum with weights, the probabilities. So that's 6 out of 9, 2 out of 3. Okay, so this is our expectation. All right, geo 1/4, what does that mean? It means it's geometric. I'm using a notation from those discrete models. It's a geometric. It's basically to model the number of the distribution of the following random variable. The random variable is defined by the following thing: the number of Bernoulli trials. Bernoulli trial means all the trials having only two outcomes. Okay, and also they're independent. Also, they have the same probability of success. Actually, there's three features of Bernoulli trials. The number of Bernoulli trials needed to see the first success. That's what this notation means. The probability of success is 1/4. So x equaling 1 means the first one is a success. 2 means the first one is failure, the second one is a success. X equaling 3 means the first two are failures and the last one is a success for 3/4 to the third times 1/4 and so forth. So f of little k equals k minus 1 failures and then 1 success. Okay. So the mean expectation is the summation of k times fk, which is this, k from 1 to infinity. This one, it needs a little bit more work. And do I want to talk about it? I will talk about it briefly. I'll give you an outline and then you can work it out. Okay. So you can't algebraically, I'm gonna just name it. Actually, I wanted to talk about this thing instead of 1/4. Just forget about 1/4 and put it back. So let's call it S. S equals this quantity. So I'm going to multiply this S by 3/4. Actually, let me list what it looks like. S equals what? K equals 1. So you have K equals 1 is 1. And then K equals 2. 2 times 3/4. And then you have 3 times 3/4 squared and so forth. Okay. I multiplied by 3/4. 3/4 times S. So you have a 3/4. Okay. Multiply this, you get 3/4. And then plus you multiply this, you get 2 times 3/4 squared. And then you have a 3 times 3/4 to the third. Okay. And you subtract. And you have a 1/4 of S here, the left side. 1 minus 0, you get, no, you're going to treat this as 0. You have 1, then I have this minus this, you get 1/4. This minus this, you get, sorry, 3/4. 3/4 squared, and then, and you'll see this is actually a geometric series. Geometric series, it's infinite. It's pretty easy to calculate. 1 over 1 minus r. So you get 1 over 1 minus the 3/4, which is so you have a 1/4. That is 1/4. That's 4. So this S equals 16. And you put back E of x equals 16 times 1/4, which is 4. This is our expectation of geometric of this distribution. Okay. All right. Let's talk a little bit about the properties. Expectation is linear in the sense that you treat it as operator. This operator is linear. That's exactly shown from this equation. So here, this is random variable. A, B is a constant. Sometimes we just say it's a scalar. What is that scalar? It's a number, okay, just a number. It's not a random variable, it's a number. And that equals A times expectation of X plus B. Obviously, expectation of any number is B itself. B is a number. All right, so this is what linearity means. Expectation of the sum of two random variables is always the sum of the expectations. All right, so it probably will take longer than I expected. Expectation of gx is defined to be the summation of g of little x times f of x. So it's actually we can talk. It's not exactly the definition. It's actually it's the easier way to calculate. In terms of definition, you actually need to figure out the distribution of gx and use the definition of a. You consider this as a new random variable y, and you get the distribution of y, and then you use the definition of mean for y. That's more complicated. So I'm gonna just treat it as a function as a fact. Okay, so that's a summation of g of little f, g of x times fx for all x. So here we wanted to calculate the expectation of x squared. I just do x squared, so -1 squared times 1 over 6 plus 0 squared times 1 over 2 plus 1 squared times 1/3. That's all. Okay, that's e of x squared. So this is pretty easy to calculate. All right, there's another concept I want to cover, which is the variance in the standard deviation. So the variance, suppose we have a random variable which has a PMF, little fx. So the variance of x is defined to be the expectation of x minus mean by expectation then squared. Okay. In essence, it's the expectation of the difference of the distance between each value of x and the mean. Okay, then you also kind of weight the sum. Yes, so let me write down the summation of little x minus mu and squared times little fx or x. Okay. This is really kind of distance. So when we talk about distance, it's usually absolute value. So maybe this would make more sense in terms of the weight the sum of distances. But this quantity is hard to deal with. Absolute value, something like that. It is a cusp here, and it's not differentiable. So this function is not very nice. So we squared it. So it's kind of a distance, but not exactly the same as distance. It's non-negative, right? Square is always non-negative. But the feature of this quantity is that I want you to see this. It's kind of variation because the distance between x value and mu, and you sum up as with some weights. So it really tells us the variation of these x values get compared with mu. Okay. Um, So the variance tells us the variability of a distribution. So if you have a distribution, so I'm gonna just use, even though we're talking about discrete, but I'm gonna use curve to describe distribution, okay? You have a distribution like this versus like that. We can tell that this has a larger variance, and this has a smaller variance. And if you have a constant that doesn't have variance, then the variance will be zero. Well, I mean, doesn't have variance, doesn't have variation, so the variance is zero. It does have variance, it's just value zero. Okay. When we use hands to calculate the variance, sometimes we use different formula instead of this one. And I'll show you how to get that and the benefit of doing this. So I'm gonna work with this quantity. I expand the square, you have x squared minus 2 times x times mu plus mu squared. We know expectation is linear, so I have 2 times mu e of x. Notice mu is a number, that's the expectation, it's a number. Then you have mu squared. But E of x is just a different notation of mu, so you have a 2 times mu squared. They are negative and positive, cancel out one of them. You have eventually this thing. I'm gonna write back as E of x squared. Okay, so a couple of things. First of all, I want you to pay attention to this fact. In general, they are not equal. This is very, very important uh, possible misunderstanding. Okay, some people equate these two things. That's very wrong. In general, they are not equal. Second of all, we sometimes call E of x squared second moment of the distribution, second moment. And E of x is the first moment. And then obviously we will have a e to the x. E of x to the third is the third moment. But normally in this class, we don't talk about third moment, fourth moment. Not a lot. A little bit while we talk about moment generating function if we do cover. So by words, we can say the variance is the second moment minus the first moment squared. Okay, so this is a sentence you can sort of memorize. Be very careful. Again, the second moment is not the same as the first moment squared. If you expand these things, you will see very clearly E of x squared is what the summation of x squared times fx for all x. Okay, and this is what the summation of fx then squared. They're very different. The inside, the first thing is actually you need to be careful. The square of the sum is not really the sum of the squares, but also it's not even squared, the sum of the squares at all because fx is not squared. But anyway, these two things are different, and you need to be very careful about that. All right. Let's see. Just how about maybe one example? Uh, let's talk about this thing. 0, 1, 2, and you have a 4 nines, 4 nines, and 1 nines, 2 successes, 1 nines. We calculate the mean for in order to find the variance. We do need to find the mean. So we figured that out earlier. That's 4 nines plus 2 nines equals 6 2/3. And then we calculate E of x squared equals 0, 0 squared, still 0. So you have 4 nines, 1 times 4 nines, plus 2 squared, you get 4 times 1 nines, and so you have 8 nines. And the variance equals 8 nines minus 2/3 squared, 4 nines. E of x squared, that's 4 nines. Uh, Bernoulli, maybe I'll talk about Bernoulli 1, 0 quickly. Okay. 1, 0, this P, this is 1 minus P. Sometimes we use PQ. Q is 1 minus P. It's just different notation. We know E of x equals P. E of x squared is also P because 0 squared 0, so it's still P. So the variance of x equals EX squared, which is P, minus E of x squared, E of x then squared, so it's P squared. So it's P times 1 minus P. Sometimes we say PQ. Okay, it's pretty easy to memorize. For Bernoulli distribution, the variance is P times Q. American roulette, let's talk about a little bit. So you have $1, negative $1. You have a 18 over 38, and you have a 20 out of 38. We have mean mu equals a negative 2 out of 38, just do that. And e of x squared would be 1 squared, so 1 is 18 out of 38, plus 1 squared, which is 20 out of 38, which is 1. So variance of x equals e of x 1, e of x squared is 1, minus mu squared, 1 out of 39. Sorry, 2 out of 38, that's 1 of 19. Then you square it. 1 out of 361. Okay, so this is the variance. Uh, the variance has the units of the original units squared. So here the mean is dollar sign, and the variance is actually having dollar sign squared. It's a little bit annoying because the variance is defined to be the summation of x minus mu squared times f of x. So you have this square thing here. All right. So it's the square of the original units, which is a little bit annoying. So that leads to another concept, which is called standard deviation. So standard deviation, usually denoted by sigma, is defined to be the square root of the variance. So now uh, the units will be the same. So we can talk about, oh, when you play the game American Roulette, you would have expected value of negative 2 out of $38 with the standard deviation of uh, this dollar. That's actually, it's about, whatever, I don't know, 19, about $1. Okay, so this is our standard deviation, and it has a dollar sign. All right. So these are the examples. Let's talk about properties. First of all, variance of any constant is always 0. Uh, A of x plus b. So first, variance of x plus b. What it means is that you're shifting the random quantity to a different place, but the variance tells us the variability. It's the sort of shape, kind of shape of this distribution of the histogram. You move around, doesn't change the shape. So the variance, the variability doesn't change if you shift around. So it's always the same as the original variance. But if you multiply by a number, then sort of you make it either uh, stretch it or you push it towards 0. Depending on the value of A, or if A is negative, then you sort of switch. But it doesn't really matter in terms of negative sign because you're squaring it. So eventually you have A squared times the variance of X. You can prove this very easily by using the the formula. Okay, variance of X equals E of X squared and minus E of X squared. You just put A of X here, A of X here, and it's pretty easy to see. You have that. So the variance of ax plus b is simply a squared times the variance of x. Okay, so you have a squared. It's again, this thing would not be negative. So this is important. The variance would never be negative. Uh, So in terms of the standard deviation, I want you to pay a little bit more attention because you take a square root and people sometimes not very rigorous and say, oh, the standard deviation of ax plus b equals a times the standard deviation of x. That is not correct. Because when a is negative, this thing is negative. That's not good because the standard deviation is never negative. So you need to go through sort of the variance. Okay, so you do this. The standard deviation of ax plus b equals the square root of the variance of ax plus b. And the variance, we can use the property there, which is a squared times the variance of x, b will disappear. And you take a square root of variance of x, we know that is the standard deviation, but then the square root of a squared is not always a. When a is positive, it's a, but when a is negative, it's actually the absolute value of a. So the formula, it would be the standard deviation of x. So you have this. Yeah, be very careful. Lastly, let's talk about this. We do have this property, okay, for expectation, you can always break it up. For variance, it may not be true. So variance, in general, they're not equal. The sum of the variances, yeah, they're not equal. Later on, we're going to talk about the situations when they are equal. For example, when x and y are two independent variables, then you have the sum, you have the equation. In fact, if they have a correlation 0, then you also have the equation. But for the moment, what I want you to uh, be aware of that is that you don't have equation for these two quantities in general. Okay, I think that's about this part. Uh, let's see anything else. Yes, that's about it. All right, and I'll see you the next time. Bye bye.